3 moles of oxygen gas are at 20 degrees Celsius. 600 joules of heat are transferred to the gas at constant pressure. Then 600 joules are removed at constant volume. What is the final temperature of the gas? Show the process on a PV diagram using isotherms and lines to illustrate each process. Let's illustrate the sequence of thermodynamic processes in a qualitative sketch. I'll begin by drawing the oxygen gas at its initial state. We have 3 moles of oxygen gas. Those 3 moles are at temperature T1, and T1 is equal to 20 degrees Celsius. The pressure in this state, P1, is unknown. The volume in this state, V1, is also unknown. Thermal energy is initially absorbed isochorically by the gas. This causes an isobaric expansion to a new state. The new thermodynamic state still has N moles of oxygen at pressure P2. Since this process is isobaric, the pressure in state 2 is equal to the pressure in state 1. However, the temperature in state 2 is unknown. The volume in state 2 is also unknown. "600 joules of heat are then removed. I will label this as Q out equal to minus 600 joules. The negative sign indicates that heat is being removed from the system. The way that this heat is removed is important. The heat is removed isochorically, which means the volume of the gas does not change during this process. The new thermodynamic state has the same number of moles in, a new pressure P3, which is unknown, a new unknown temperature T3, volume remains constant since this is an isochoric process, so the volume of state 3 is equal to the volume of state 2, which is unknown. There are a lot of unknowns during these processes. Our goal is to find the final temperature of state T3. To help us find this temperature, let's represent these processes on a single PV diagram. In state 1, the gas has pressure P1 and volume V1. It then expands at constant pressure to state 2, which is still at pressure P1, but at a new volume V2. After the expansion, thermal energy is removed isochorically until the gas arrives at state 3. We have two ways for this process to occur. The process can either occur by an increase in pressure or a decrease in pressure. As long as no work is done on the gas, removing heat from the gas will lower its temperature. This lower temperature lies on an isotherm below the isotherm that state 2 lies on. So this corresponds to a decrease in pressure. So from 1 to 2, heat is added to the system, and from 2 to 3, heat is removed from the system. Now that we've established that we have a decrease in pressure, let's see what we have to work with. So in order to find the final temperature of the system, we need to know how much the temperature changes during each thermodynamic process. Once we know the temperature changes, we can then add them to our initial temperature to find the final temperature of the gas. We know that the heat added during the isobaric expansion from state 1 to 2 is given by the Molar specific heat equation, which is the number of moles in times the gas's specific heat at constant pressure times the change of temperature of the gas during this process. The molar specific heat for oxygen at constant pressure is 29.2 joules per mole Kelvin. We can use this information to find the change in temperature between states 1 and 2, which is equal to the heat added during the transition from state 1 to 2 divided by the product of the number of moles and the specific heat of oxygen at constant pressure. This is just the heat added to the system divided by NCP. To find the change in temperature during the isochoric decrease in pressure between states 2 and 3, we can use the molar specific heat equation at constant volume, which is equal to the number of moles times the gas's specific heat at constant volume times the change of temperature of the gas between states 2 and 3. The molar specific heat at constant volume for oxygen gas is 20.9 joules per mole Kelvin. This allows us to express the change in temperature between states 2 and 3 as equal to the heat removed from the system during its transition from state 2 to 3 divided by the product of the number of moles and the specific heat of oxygen at constant volume. We now have enough information to determine the final temperature of the gas. The final temperature of the oxygen gas in state T3 is equal to its initial temperature plus the changes to its temperature during the isobaric process from state 1 to 2 and the isobaric process from state 2 to 3. Substituting our expressions for the temperature changes, we have T3 equal to the initial temperature T1 plus Q added over NCP plus heat removed divided by the number of moles times the molar specific heat at constant volume. We have expressed the final temperature algebraically in terms of the variables that we know, so we can now plug in numbers. T3 is equal to 20 kelvins plus 273.15 Kelvin. This is just the given 20 degrees Celsius converted to the Kelvin temperature scale. Plus 3 moles of oxygen gas whose specific heat is 29.2 joules per mole Kelvin. This is under 600 joules of heat added to the system. We then add the heat removed from the system term, which is 3 moles of oxygen gas at 20.9 joules per mole Kelvin for the specific heat at constant volume, under 600 joules of heat removed from the system. Let's do a unit check by canceling units. Joules cancels with joules. Moles cancels with moles. This leaves us with Kelvin, which is what we would expect for the temperature. Since there are additions and subtractions, let's keep track of the precision of our terms so that we can add them and subtract them by using the proper rules of addition and subtraction and significant figures. This first term is 6.85 Kelvin. The last term is equivalent to minus 9.57 Kelvin. Even though I've written the rounded values of 6.85 Kelvin and minus 9.57 kelvins, I am actually only using these values as placeholders to see what their precision is based on the rules of significant figures. Since 20 Kelvin is the least precise number used during the addition of these terms, we will need to round our final answer to the tenths place. In my calculator, I'm not entering the rounded numbers. I'm entering all the algebraic steps you see here and will take my final answer and round to the tenths place. After doing this, I calculate that the final temperature of the gas is 290.4 Kelvin, which is equivalent to 17.3 degrees Celsius. We should ask ourselves, does this answer make sense? That our final temperature is less than our initial temperature? Let's give ourselves a reality check by adding the isotherms on which each of the 3 states lie to our PV diagram. State 3 has an isotherm T3 that looks like this. State 1's isotherm T1 is above the T3 isotherm based on our calculations. State 2's isotherm is above T1's and T3's. This must be true since isotherms do not intersect. So, from the sketch of our isotherms, we see that in the transition from state 2 to state 3, the gas crosses the T1 isotherm at 20 degrees Celsius on its way down to T3 at 17.3 degrees Celsius. This makes sense, so we should feel good about this result.